Forrest Glebe from the University of Hawaii. We'll talk about Frobenius non-stability of Nilpotent groups.
Thank you. Thanks for the introduction. Thanks for having me. Let's get started. So I will, review what the Frobenius norm is. Okay. And I will denote it with a 2, and when I have no subscript, that will be the operator. So to distinguish this from the Hilbert-Schmidt norm, this is the unnormalized trace instead of the normalized trace. And this is also just the L2 norm of the entries of a matrix. And I think it's interesting because if you asked like a linear algebra student, to come up with the norm on a matrix, this is probably the first thing they would think of. Even though it doesn't have the same sort of, connection to probability spaces as the Hilbert-Schmidt norm, I think it's interesting in how simple it is. And it's maybe the non-commutative analog of the L2 norm with the counting measure instead of the probability measure. And I like both, so. Okay. So, Frobenius stability. So defined the same as Hilbert-Schmidt stability or operator norm stability, but with this norm instead. So I guess this would be the local-to-local stability from Marius's talk. I'll probably have to move it back down again. Okay, so this was introduced by Deschiffre, Glebsky, Blavatsky, and Tom, and in the paper they use it to live the dream of actually showing something is not approximated. So, I guess the main theorem I'm going to talk about today is that most finitely generated nilpotent groups are not stable in this. So, so a finitely generated nilpotent group, it's going to be Frobenius stable if and only if then the condition is that it's virtually cyclic. So either it has a finite index subgroup that is Z, or it is itself finite. So if follows from this group of authors, I'll focus on only if. And I guess to put this in some context and show a good chunk of you your own names, maybe I'll get one for the board. So a lot of these theorems are much more general than just for nilpotent groups, but I'll just focus on nilpotent groups. So they are permutation stable. They're also Hilbert-Schmidt stable. Oh no. Crossing the halfway, whatever. But in the operator norm, it's the same as the 2 norm. So I guess this shows us that the unnormalized 2 norm, at least in this case, looks more like the operator norm than it does like these normalized ones, which is, maybe is surprising at first since the Hilbert-Schmidt norm is defined similarly. But if you think about it a little more, this norm is big and the operator norm is also big, so that's why it acts more like the operator norm. Okay. So I've left myself an awkward amount of space, so I'll just go over here. All right. So first, I want to explain what happens for the simplest example, which is z squared. Okay. So I guess we've seen these a couple of times. So we have Voiculescu's example, and he was thinking about operator norm instead. But if you think about it, it also works for both, which I'll show in a second. So UN cyclically permutes the standard basis, Vn, all the nth roots of unity in order kind of on the diagonal. Oh yeah, I guess I should say what it is. So omega n is this primitive nth root of unity. And so I forgot about my color coding. So imagine these are in yellow. Okay. So to show that these actually approximately commute with each other in the 2 norm, so the 2 norm is dominated by square root of dimension times the operator norm. And we have seen that this defect in operator norm is less than 1 over n. Or 2 pi over n. The multiplicative commutator of these is the primitive nth root of unity, and that gets closer and closer to 1 at sort of a rate of 1 over n. And that's by unitary invariance, that's the same as the defect of the additive commutator going to 0. And we can see this n in the denominator and the square root of n, the n in the denominator, it wins. So this goes to 0. Okay? So why are these far in the 2 norm from things that actually commute? Well, it's because they're far in the operator norm and the 2 norm is bigger. So and so then the winding number argument that we've already seen is how you would show that these are far in the operator norm from any 2 things that commute with each other. And so since the 2 norm is bigger than the operator norm, they have to be far there as well. So I guess my color coding will be that this yellow is how you actually make an almost representation and show that it is almost multiplicative. And orange will be how you show it's far from an actually multiplicative thing. And so the point I want to make here is if you have an example that works in operator norm, this part is kind of trivial, right? Like if you already know your example works in operator norm, then this orange chalk part of the proof is trivial. You just say the 2 norm is bigger. But the yellow chalk part, we actually have to know something specific about this example. We have to know that defect in operator norm is like 1 over n, and we have to know that the dimension is n, otherwise this square root, if you had a bigger dimension, this square root of dimension could mess everything up. Yeah?
Is it known whether z squared is 1 norm stable?
Good question. So it is, it's not in the literature, but Ozawa has sent, at least to me and I think to some other people, a sort of 1-page write-up that shows that it's not.
Is not 1 norm stable?
Yes.
So you can construct matrices for which this defect?
Yeah, so you can't use the winding number argument, but it's like sort of a purely analytic argument.
But the problem here is that these are not 1 norm multiplicative, right?
Yes, yes. So these are not 1 norm multiplicative, but he makes another example.
Okay.
Yes, so I guess speaking of other Schatten P norms, this theorem, it's true for every P strictly greater than 1, but I'll maybe only verbally mention that and just focus on the 2 norm. And you can see this argument also works if you replace this with any P greater than 1. This would still go to 0, and it doesn't work for the 1 norm. Okay. So, so I guess the kind of intuitive thing is we know, how you'd want to prove this is you know that most of them are not stable in the operator norm. So you can kind of check an example. Unfortunately, this proof is not constructive, so there isn't an example to check. So we're going to try to prove this constructively and then check if the examples work. And we can get it so that they do. But I guess I'll warn, in this, for nilpotent groups, Frobenius stability and operator norm stability are similar, but they're not equivalent in general. So there are examples. Due to Bader, Lubatsky, Sauer, and Weinberger. Of Frobenius stable groups that are not operator norm stable. And so that shows that this yellow chalk part of the proof, it is actually non-trivial, right? It is actually non-trivial to find an example that's asymptotically multiplicative in the 2 norm. And the type of cohomology that shows up in Marius's proof in this case is two cohomology. So I'll point out relevantly that some of these examples, they even have a non-torsion 2 cohomology. So it is, really something special about nilpotent groups that makes this work. Okay, so all right, so as I mentioned, we have this nice example that sort of kills two birds with one stone, right? We get the operator norm and the Frobenius norm for free, and we know the operator norm bird is dead, so let's find the murder weapon and see if we can use it to kill some other birds. So I have a theorem for that. So we have a finitely generated group. And a non-torsion element in the 2 cohomology. And we'll represent it as a central extension, which I will explain in a little bit. And then we're going to assume that this middle group is residually finite. And I apologize, I probably wrote this a little too small. I will, maybe I'll just, okay, so this is the if, sorry to put the then on a separate board. So if this is true, then the group is not operator norm stable. And the other thing you can do you can find an explicit counterexample. So just knowing that it's not stable, it might not follow like literally from Marius's theorem how it's written, but it morally follows from the techniques. But the new thing is we can actually write out what these are. Okay. So for some of you, this is probably a review. But let's talk about what we need to know about 2 cohomology to make this work. Okay. So here I'll have coefficients in the integers. So any 2 cohomology class, you can represent it as a short exact sequence. And then what does it mean that this is central? It means that the image of this copy of Z is in the center of the middle group. Okay. And so to connect this to a picture you might have already seen, so this, you can imagine you have sort of a wrong way map. So this is a set theoretic section, meaning if you go up and then back down, you have the identity, and this is not actually a group homomorphism, which will be related to the fact that these examples are far from actual group homomorphisms. And then we can use this to define what's called a 2 cocycle, which is maybe another way you might have seen 2 cohomology be expressed. So we measure how badly this fails to be a group homomorphism. And by exactness, this is in this image of Z. And we can abuse notation a little bit to say it's in Z, because iota is injective and it'll be in the image. Okay? All right. Good place for questions. All right. So, another ingredient. It'll be orange because we'll use it to show that our examples are far from actual representations, is 2 homology. So I'll introduce what's called the Hoff picture of 2 homology. So suppose our group is a free group mod some relations. Then we can think of the 2 homology as relations on the group that can be written as products of commutators. And then we mod out by some trivial ones. So this R, you think of this as the group of relations on your group, and you want to take the ones that are commutators. So why is that, connected to stability? So we took this winding number of this path, so to show Z squared is not stable, you make this path where you go from the multiplicative commutator of your 2 almost commuting things. So you have this path of matrices, you take the determinant, and you show that this thing is non-zero, and if you put in commuting things, it would be 0, and since it's a winding number, there's sort of a homotopy invariance. Well, if you replace this multiplicative commutator with a product of commutators, it still works. So really, secretly, this argument is capturing something to do with the 2 homology of the group, which Marius has made formal. And I guess the type of winding number argument I actually use in the proof of these theorems, it uses the bar resolution instead of this, but it's the same. Marius and I have checked. Okay. So, all right, I'll try to, I'll just ignore these. Okay. let's put these pieces together and make an explicit example in operator. Okay. Maybe I'll save this for the end. Okay. So we start with our central extension. Okay. And we'll have a wrong way map, which really should be yellow and orange, but I'll make it orange to make it stick out. And we assume this is residually finite. So it has a bunch of finite quotients, and if you figure out the image of one, it's going to be finite order because the group is finite. And that will induce finite quotients on the group you started with. Okay? So let's give this a name, and give this also a name. Okay. So what we're going to do is we're going to start with the character on this thing. So it's a one-dimensional representation. And this is going to go, I still have it up to this primitive root of unity here. Okay? So now we're going to take an induced representation to get a representation of this. Great. So we start with a representation of a subgroup, and we want to build one of the larger group. And induced representation is a tool that lets us do that. And because this is central, it will actually take the image of this copy of 1. It'll go to an amplification of this. So this primitive nth root of unity times the identity. Okay. So then, I guess in this case, a sequence of more and more multiplicative things, we can define it as pi n composed. So this map that goes down to the finite quotient composed with this wrong way map that's not multiplicative. So why is this asymptotically multiplicative? So the failure of this thing to be multiplicative, it lives in the copy of z. And if you think about what happens to this copy of z, the generator, it goes down here, and then the induced representation takes it to this primitive nth root of unity. And that's still true when you induce it back up there. So that means the failure of this thing to be multiplicative, point-wise, it gets closer and closer to the identity. So it's asymptotically multiplicative. Why is it far from things that actually commute with each other? Well, this is a non-torsion class. So the universal coefficient theorem tells you that this must pair non-trivially with a two homology class. And that means there's some balanced relation in the middle group that's not true in the group we started with. And what that gives us is that we can run the winding number argument on that relation, and we will get that we're far from an actual representation of the group, or in particular anything that satisfies that specific relation. Okay. All right, another, I guess, natural stopping point for questions. Yep.
Do you have a guess what would happen for virtually nilpotent groups?
Oh, for virtually nilpotent groups? So like for example, infinite dihedral group cross Z looks a lot like Z squared and is virtually nilpotent. It is stable in operator norm. I don't know whether or not it's stable in the 2 norm, but this technique will not work. Infinite dihedral group cross Z. This is one of the groups cross with Z. Yeah, one of the groups that Euler, Schulman, and Sorensen have shown is operator norm stable. So this technique will certainly not cover all virtually nilpotent groups because it would also show that they're not stable in operator norm, and that's not true. Yep.
So all of your counterexamples all factor through finite groups.
Yes.
Okay. Is that common? I mean, I don't know if I've.
Yeah. So So I guess I'll say it like this. If you have sort of a nice formula that comes from a central extension, like it's an actual representation of this group, then by Malsev's theorem, if everything is finitely generated, the sort of group that those matrices make will be residually finite. So it will necessarily then factor through finite groups. I guess there must exist things which don't factor through finite groups, but I don't think it will be possible to get sort of like it won't be possible to get them to be exact, representations of this thing. And I don't think you'll be able to get like a nice, pretty formula for it that is easy to write on a chalkboard. But maybe you could get some kind of bad, ugly formula, but I don't know how to make it. Any more? Okay. So, where was I? Okay. So, what happens if we try to apply this recipe to Z squared? So you would want to get Wojciechowski's example back.
Sorry, can I ask another question?
Yeah.
So like in these examples, so you go back with this data and then you project back, but so for gamma tilde, like on gamma tilde, these are all homomorphisms. Is that right?
Yes.
Okay.
Yes.
Yeah.
So these will give you genuine representations of the middle group.
Okay, and but gamma tilde, is not saying that gamma tilde is stable. I mean, it's just saying specifically.
It doesn't say whether or not gamma tilde is stable. It might or might not be. Okay. So actually, maybe I'll leave this up because we're gonna explain what happens here for Z squared. Okay, so sort of the natural family of finite quotients of Z squared is going to be Z mod n cross Z mod n. And one way you can kind of build the induced representation okay. And I can write out for you what this is. And in a perfect world, we would like this to be this example. But you can already tell the dimension of this is n squared, not n. So let's see what happens. Okay, so an element of Z squared is a pair of integers. So to define this, I'll say what it does for a pair of integers. And this is L2 of Z mod n tensored with itself. So I'll use this tensor notation. Okay. So I'll change these to be j and k. So I can be the square root of -1. Okay. So if you ignore this exponential, this would just sort of be the left regular representation of z mod n cross z mod n. We translate the coordinates over by a and b. But now we've twisted by this. And so we have this b times j. So that's a function that takes in this element of z mod n, or z, which you can kind of think of as coming from the finite quotient because it factors through. And then we take this other element of z. So the 2 cocycle that this comes from is this. This generates the 2 cohomology of z squared. And so this b times j, this is coming from the second copy of z, and this is coming from the first copy of z. So we're really taking this left regular representation, and we're twisting it by the 2 cocycle. And so you can ask, does this work for Frobenius norm? Well, no, because the defect of being multiplicative is like 1 over n, and the dimension is n squared. So, you know, what can we do? Well, we know that this should work because there is an example. And I guess this should also be yellow, but I want it to be a different color, so white. What you can do is you can just ignore this second tensor coordinate. And you see that the element in the twist, it doesn't see the second tensor coordinate. What we do to the first tensor coordinate doesn't see the second tensor coordinate. And so suddenly we get something that's still sort of well-defined and almost multiplicative. And now instead of the dimension being n squared, it goes down to n. And so now we've made something that does work for Frobenius norm. And I don't have like a really good abstract motivation about why this works. It just, you know, I looked at the examples and it works. You know, what else is there to say? So, and it does in fact turn out when you ignore these second tensor coordinates, you do get back to Wojciechowski's example. And I guess maybe a theoretical reason why the naive thing doesn't work is induced representation is defined to be like a maximal object. And really what you would want is a minimal object, but there's not like a canonical minimal thing. So we're kind of left with this canonical thing not being the most efficient thing, and so we have to find a sort of smaller, more efficient thing. Okay. Okay. So to prove this main result, I don't think I mentioned this earlier. It's enough to show the torsion-free case. And to reduce to the torsion-free case, I do a lemma by Bader, Dvotsky, Sauer, Weinberger. So I won't write it out, but what this says is that if you have, well, okay, so I guess a basic group theoretic fact is that the torsion elements here, they make a finite normal subgroup. And, oh, I might get the implication wrong, but the contrapositive of what they say is that if when you mod out by a finite normal subgroup, you're not stable, then the original thing is stable. So they're using this to prove that things are stable, but I'm using the contrapositive to go the other way. All right. So We've seen finitely generated nilpotent groups enough times, so maybe I can abbreviate it. So torsion-free finitely generated nilpotent groups. They have a natural coordinate system. So you can describe them with tuples of integers, which I guess is technically true for every countable group, but this actually does it in a way that just tells you something about the structure of the group. And so a result of Philip Hall says that, what do I mean multiplication is given by polynomials? You take in two of these tuples of integers, the multiplication should get you out a tuple of integers, and a result of Philip Hall says that the function that does that is a polynomial. Which I think is not strictly necessary for what I'm going to say next, but maybe just to convince you that these coordinates, actually tell you something about the group. Okay. So I guess I'll cut this theorem in half by erasing inclusion. Okay. So suppose we have a cocycle. I guess we're bad at naming things, so it's skinny, and now that I'm on the board, I'm forgetting skinny has an E in it. What? Either way. I don't know if this is a great name, but I guess we've established that people who do stability are bad at naming things, so there you go. So you want to represent it as a two cocycle, so that's going to be a thing that takes in two elements of the group and gives you an integer. So this is going to be a sigma of x and y, and then these are both m tuples of integers. So it's a function of all the coordinates of x and only the first coordinate of y. And you can see this cocycle has this property. And if you think about it, the fact that it has this property is why we don't have anything that depends on the second tensor coordinate here. And that's why we can just, cross off this second tensor coordinate.
You put the coordinates in some canonical form, like that y is something outside the commutator, or?
Yeah, so,
You don't care.
So, yeah, good question. So I guess the structure is, these should all be powers of elements, and then the last one maybe is in the center, and when you mod out by that, the second to last one is in the center, and when you mod out by that.
So the first one are always
yeah, so the first one
coordinates for the commutator quotient.
Yes. So in particular, the first two coordinates are actually group homomorphisms to Z, but the third and beyond are not in general homomorphisms to Z. Does that actually answer your question?
Yeah, that's
Okay, cool. Right, any more? Okay. Okay, yeah, so I guess to motivate skinny, you know, it doesn't take as much space this way on the board because we can stop writing the y's here. Okay. So supposing we have one of these, sort of following our more efficient example for z squared, let's say where this goes. So now this is going to u of n. So we've gotten the dimension down to n. And maybe we'll think of u of n still as little L2 of z mod n. So this is, you know, the basis is indexed by z mod n. Okay, so now we're gonna twist by this cocycle, and we have one whole group element to feed it, and then we don't, you know, in a abstractly you would want to feed it a second group element, but actually we only need to give it one coordinate, and that one coordinate can be the j. I guess really this is in z mod n, but you know you pick whatever representative, and it shouldn't end up mattering. Okay, and then we shift the coordinate over by x units. So this is kind of a generalization of this. Okay. So this is a formula, and then of course the punchline is that these types of cocycles actually exist. So FGN, again, finitely generated nilpotent. Okay. So I guess I'll just verbally say a few words about how I prove this. All right, so you start, sorry, I forgot to say, non-cyclic, sorry. So Z in the trivial group, of course, don't, but the rest of them do. So how I prove this is just like induction on the Hirsch length, which is in this case the number of coordinates. So you start off with z squared, here it is, and you kind of have to split into cases. Either the pullback of the one you start with is non-torsion, in which case you can take that, or if the pullback is torsion, there's a much more complicated thing where you can like build another one. And, you know.
Is something missing in there? And with your EXP, it seems like there's nothing.
Oh,
like for n, like it's supposed to be like smaller or something for n, like the.
uh,
like it's supposed to divide.
oh, yeah. Oh, divided by n. Yeah. Thank you. Yes. Yeah. Yes, divided by n. Right. And I guess it does implicitly depend on, well, yeah, divided by n. Thank you. Right, which makes it more multiplicative. And then I guess, yeah, relevantly, this is going to 1, like 1 over n, and the dimension is n. So by the same computation, it's multiplicative in the 2. Okay, so yeah, so you build this by induction on the Hirsch length, and that shows, so, okay. So I have a few minutes. So a natural question is, could higher cohomology obstruct Frobenius stability? And to advertise a recent result of mine, it shouldn't. I will briefly explain. So in Marius's proof that cohomology obstructs stability, you can sort of view the invariant like this. So we have something sufficiently multiplicative in operator norm. We make this vector bundle over the classifying space. This is morally true for any group, literally true when the classifying space is compact. So you can take Chern characters. The 0th one doesn't tell you anything interesting, but then the other ones, they're orange, which means that if they're non-zero, you're far from an actual representation. And then they keep going to all the even cohomology classes. So, so a recent theorem of mine says so if we throw something that's sufficiently multiplicative in the p norm into this, it's because the p norm is bigger, also multiplicative in the operator norm. So we can take all of these invariants, and the first one, like Marius mentioned, is sort of equivalent to the winding number argument. And the higher ones, you know, if they're non-zero, they show you're far in operator norm from an actual representation. So they should also show that in the p norm because, once again, the p norm is bigger. So in principle, these can all tell you about the p norm. So what happens if we put something sufficiently multiplicative in the p norm into this machine? Then for every k greater than or equal to p, this invariant is 0. So in particular, if you put something multiplicative in the 2 norm into this, this one is allowed to be non-zero. But then the second Chern character, the one in 4 cohomology, now we have 2 greater than or equal to 2, so this one is 0, and all the higher ones will also be 0. So you know, I can't prove there's no sort of subtle argument that connects higher cohomology to Frobenius stability, but at least these topological invariants, there will not be useful tools for Frobenius stability, except for this one. All right, thank you.
All right, thank you, Forrest. Are there any questions?
Can you explain where this k greater than or equal to p comes from?
Yeah, so basically, so this bundle, I think Marius mentioned the term almost flat in the operator norm. So you get something that's almost flat in the p norm. And there's a formula for this thing of, so this is the curvature form to the k. Oh, I should not have used, capital and lowercase k together. Maybe F for form, I don't know. Okay. You normalize, I forget exactly what the normalization constant is, but we take this curvature form that is like small in the p norm, and now let's just say it's small in the Schatten k norm because that's the way the inequality should go. That means by Holder's inequality, when you raise this to the k, you get something small in the 1 norm. And then as this gets smaller and smaller, the trace is kind of continuous uniformly in n from the 1 norm. So that means this thing has to go to 0 when it lives in sort of a discrete space. So eventually it has to be 0. So I guess the short answer is it comes from Holder's inequality to go from the p norm to the 1 norm.
Any other questions?
So why exactly you used, I mean, I understood that you used properties of this norm, but why exactly that it is specifically this norm?
Oh,
Maybe you can put like conditions, just I take any norm, submultiplicative,
Oh, yeah.
this inequality, and then everything is kind of...
you mean for this theorem or for
yes,
this theorem?
for
this
the
one.
first.
Yeah, so this works for every unnormalized p norm with p greater than 1 and the operator norm. So it's not really that specific to the 2 norm. Like you said, you could put some inequalities on it like that.
But even without precision, which norm? Just say conditions on a norm.
Oh, yeah, I think so. Like, you would want it to be bigger than or equal to operator norm, and less than or equal to operator norm times like dimension to some power less than 1, I think.
And submultiplicative, right?
Not necessarily, because it
Okay.
just has to be sandwiched in between the operator norm and the something depending on n times the operator norm.
Right, so if there's no more questions, then let's thank Forrest again.